What's going on, folks? We're hitting up chemistry today, and I have no idea why I start every class with what's going on, but I just think it is kind of my thing. I don't know. Every time you start up the YouTube video, it starts off with, "What's going on, algebra students?" or "What's going on, chemistry people?" Anyway, that's my thing. Yes, I'm going to record. I started the YouTube recording. Now I'm going to start the Canvas recording, and we are double recording this thing. What are those folks? What's going on, folks? The folks being you, students. All right. We talked about the conservation of mass. We talked about the law of definite proportions. A lot of this stuff you can read inside of your class. I do want to cover some other things. The math today is not as heavy. All right, we talked about this. We talked about atoms. We thought that atoms were identical. They're not. Then we had Gay-Lussac's. All right. Now, Gay-Lussac, what he did was he came up with this idea of pressure and volume in gases. And so he's talking about the pressure of atoms increases as the temperature increases. I think that's what it is. Yeah. And then Avogadro came up with his own hypothesis, and he says that if a gas is at the same exact temperature and pressure, and they have the same volumes, but they're different gases, it contains the same number of particles. And so Avogadro, later on you're going to learn this thing called Avogadro's number, and it's a really big number, and I forgot it. I think it's like 6.022 times 10 to the 23rd power. Anyway, it's some number that's stuck in the back of my mind when I did chemistry like 10 years ago. But it's a really important number, and we'll go into that. But basically, Avogadro was this great scientist that was really important to this thing. All right, here we go. J.J. Thomson. Let's talk about this. He was actually an English physicist. And I hate to say it, but a lot of these guys who are really big chemistry people, this is why physicists always are pompous and I can say this because I'm a physicist, but they're always going to say, well, the only true science is physics. Everything else is just stamp collecting. Would you like to know why I can say that? Because one of the godfathers of chemistry, Ernest Rutherford, who we'll learn about, actually said that. So J.J. Thomson was a physicist, even though he contributed to chemistry, and in this way. What he did was he was working with cathode ray tubes. He wasn't working with lasers, because this was back in 1898 or 1903, but he was working with these cathode ray tubes. And they look kind of like this. It's a cathode ray tube. Got it? Now, he postulated that there's a stream of electrons that is kind of flowing through here. And in his cathode ray tube, there was a negative side and a positive side. And what he noticed was this. He noticed that the beam of light would kind of bend. Let's make the beam of light green. It kind of bend when it's approaching the negative side. Now, why do you think that would be? By the way, Bradley, I think that the T and P were the temperature and pressure. Because of physics. Okay, but why in physics? No, it's not a beam of light. He noticed that the beam inside of the cathode ray tube bent as it approached the negative side. It didn't do it to the positive side, just the negative side. Tejas is right. Because he postulated that this beam was made up of this thing called electrons. And it must be that electrons were what kind of charge? Positive or negative? Kai is right. It would be negative. It must be that these electrons, these supposed electrons, were negative. because they kind of deflected whenever they hit a negative thing. Does that make sense to you? So he came up with this idea that he called plum pudding. It's an English dessert. I don't know what the deal is. Anyway, it's like, I guess it's like, people don't really give those in Hawaii, but like fruitcake, you know, kind of like it's like bread with like little rice, or not rice, but raisins in it, I think. It's bread pudding with raisins all over it. Actually, you know what? Let's look up what plum pudding looks like. Plum pudding. I love the word, so I just keep teasing it. Here, let's see. Plum pudding. Images. Oh no, it's not plum. It's plum. P-L-U-M. Plum pudding. All right, this is a nice picture. This is a nice picture. I like this one. All right, it looks tasty. All right, here's plum pudding. Now, what plum pudding is, it's bread with these kind of like raisins, fruity things that is kind of like intermixed, dispersed in within, and it's also covered with a fresh thing of raspberries and some kind of sauce. I have no idea what the sauce is, but it looks like what I put on my Cinnabon, so I'm down with that too. But here's the thing. Don't worry about the sauce or the raspberries. Think of the raisins inside of the bread. He came up with this idea called the plum pudding model. And what he said was, he said that electrons are these negatively charged things, and that's what the raisins are inside of, you know, atoms. And atoms have a basically kind of like overall positive shell. So the shell is positive. Let's make the shell red. The shell is positive. It's kind of like a smear of positive charge. And then the raisins are negative. The electrons are negative. And that's what J.J. Thomson postulated. And then what he did was he was able to kind of calculate out some numbers and get a good understanding as to, based off of these numbers, I calculate out the size of an electron to be, okay, wait, I didn't write it down. Let me look it up. It was, what was it again? It was something times 10 to the negative 20 something. I forgot what it was. I don't memorize any of these numbers, but I do know how to look them up. J.J. Thomson postulated that the electron was, the charge to mass ratio was negative 1.76 times 10 to the 8th power coulombs per gram. All right. And he calculated that these electrons are very, very small. Represent physics. Yeah, exactly. Okay. There's this other dude. His name was Millikan. And he came up with the Millikan drop experiment. Any girls wear perfume in this class?
I think all girls do.
All right. All right. So all the girls in this class wear perfume. I'm not talking about deodorant. I'm talking about perfume. Now, the old school perfume bottles, they were like, I mean, this is old school. You don't even use them anymore. But I think maybe you may have seen them in movies. They're like a bottle right here, and they've got like a nozzle right here, like this. And there's a little ball right here, and you squeeze the ball, and it goes. Tss, 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 tss. Have you seen that before? Yeah, like a perfume spray thing. Right. You have a bottle like that? That's awesome. That must be really cool. Anyway, I think it's called an atomizer or something like that. Is that what it's called? I don't know. Anyway, Millikan came up with this idea. He said, what I'm going to do is I'm going to take a perfume bottle spray, and he's out of the University of Chicago, and he sprays a mist over here, like that. And then what he does is he sprays a mist of electrons that are over here. And then those electrons will fall through a cavity over here. And it will fall like this, dot, 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 in a single line right there. And he takes a microscope and he looks inside of here. Here's his eye, looking at in a microscope like that. And what he did was he was able to vary the charge on these electrons and have these things fall at a slower rate or a faster rate, depending on how he changed the magnetic field inside of this thing. Am I speaking crazy here? Or does this kind of make sense to you? When I remember Millikan, I think of the perfume guy. To be honest with you, that's why I brought up the perfume thing. But anyway, all right. So, what he was doing is he is able to calculate out how massive or not massive the size of an electron is, and he said, okay, well, based off my experiments called the Millikan drop experiment, I calculate the mass of the electron to be 9.11 times 10 to the negative 31 kilograms. Is that big or small? Small, yes. It's incredibly small. It's super small. In fact, it's like uku plenty small, right? How would we say that in Pidgin? Like manini. It's like manini small. All right, anyway. It's super small. So here's the thing. This dude named Ernest Rutherford came along, and he came up with a really cool experiment, and I'm really down with this experiment. By the way, let me see if I have a nice picture. Oh, I don't have the Millikan drop experiment. It's still loading. I don't know what the deal is. Ernest Rutherford. I really like what this dude did. All right. So, here's what Ernest Rutherford did. Ernest Rutherford is actually a physicist, and he was quoted with saying, and I love this quote because I'm a physics major, and you won't get this from any other chemistry teachers, but the only true science is physics. Everything else is stamp collecting. He also won the Nobel Prize in chemistry in 1908. I love the irony of it all. But this guy was a physicist as well. And so what he did was he said this. Okay, if the electron or if the atom looked like this picture where it was a plum pudding model, right? Where it has this smear of positive charges. And it has, actually I made my smear red last time, yeah? It has a smear of positive charges, and it's got negative charges interdispersed in here. And he also figured, these negative things are really small, right? Because he read Millikan's experiment. And his wife wore perfume, so he was able to do the experiment himself. No, I'm kidding. I don't know. All right. What he said is, if I shot negative particles at this plum pudding, what would happen? So what he did was he took out some kind of filament, a detector, and he put it around here. Okay? And then he said, I'm going to take a negative electron and shoot it into this thing. And here's what I think will happen. The electron will go over here, and if it comes close to this small electron over here, what will happen is it will deflect. So it won't go straight through, but it will go almost straight through. Does that make sense? All right. And then this one will come in, and maybe it might hit this thing dead on, but that thing is so manini small that it will only deflect it a little bit. Does that make sense to you? So he kept shooting these things at this plum pudding model. And he said, if that's the case, this must be what will happen. All right, so he did the experiment, and here's what he got. When he shot the negative electron over here, it did exactly what he thought it would. It deflected a little bit, sometimes. Some of them went straight through. You guys got it? All right. But when he shot the thing towards the center of it, and it's hard to discover exactly where the center of an atom is, but I mean, when he shot the thing, what happened was he started getting traces out here and traces over here. and traces over here. What the heck is going on? Give me some suggestions. You're Ernest Rutherford, you're doing this experiment, you're from New Zealand, you're on a scholarship to Cambridge University, and you've discovered this thing. What the heck is going on? It's hitting something. Ah, yes. Yes, it is hitting something. Oh, and I apologize. I'm sorry. They weren't negative electrons. They were actually alpha particles. So they're positive. They were positive things, not negative. Sorry. It's hitting the almost center and then bounced. Okay. It's hitting something. I agree completely. And that's where Ernest Rutherford said, I disagree with J.J. Thomson's plum pudding model, and what I'm going to suggest is it's not really a plum pudding. What it is there's got to be some kind of like core in the middle that is positive. And then outside, there's these small negative things that kind of roam around in a cloud. And it's not neutral because the positive thing that's coming in hit here and bounced off that way. I should have made that red, by the way, but I'll make it black. The positive thing coming in here hit and repelled against here. But when it went over here, it only got slightly deflected. Because it was only interacting with the electrons in that case. So he said, there's got to be, it's not that this positive part is spread out as a smear over this whole thing. It's that there's this concentrated small core in the middle. Does that make sense? And from that, he came up with this idea. Now, I can't believe that you guys didn't figure this one out yet. This would be the protons, and then it's the nucleus of your atom. An atom has a nucleus. It's got electrons. Electrons are floating around in a cloud outside. The nucleus is a really small, concentrated part of the atom where your protons and neutrons exist. And it wasn't until Rutherford till we had a very clear picture of that, and he did this experiment. And he thought it was going to show up like this, and it didn't. It showed up like this all over the place, and he was like, what the heck is going on? It's because there was this solid core in the middle that was bouncing them out. It's because of the nucleus, exactly. So that's the story of Rutherford. Are we cool with that?
Yeah.
I love that story. It's one of my favorites. All right. So from that, we have a much better picture as to what a molecule looks like. And it wasn't until Rutherford came where we said, an atom is no longer a positive smear of charges. An atom is a dense center of positive charges that we call a nucleus. Electrons travel around the nucleus at a relatively large distance. That's what he's saying. He's saying that it's a small, incredibly dense piece of, things. Now, how dense is it? Okay. What do we know about atoms now and the atomic structure? Well, we know an atom contains electrons, it has protons, and it has neutrons. The protons is found inside of the nucleus. It is a positively charged, equal in magnitude to the electron's negative charge. The negative charges come from the electrons. The neutral ones are in the nucleus is called neutrons, and they don't have any charge, but they are about the same size as the protons. The electrons are way smaller than the protons and neutrons. We cool with that? All of this information is important information to know. I almost feel like you understand this information. There's a little table inside of this in your book, and I think that is important. But the nucleus it's small compared to the overall size. For example, if the nucleus was the size of a marble, and you took that marble and put it in the middle on the 50-yard line in the middle of the field of Aloha Stadium. Can you guys imagine Aloha Stadium in your heads? And you take a marble and you put it in the middle of that. That's the nucleus. Your electron would be a speck of dust on the outside in the parking lot. And everywhere in between, there's a bunch of space. That is what all atoms are made of. It's a very small core in the middle. But it's extremely dense. Even though it's so small, it's an extremely small piece of the atom. It is extremely dense. And here, let me tell you what it is. If you take just a bunch of nucleuses and make up some kind of substance that's the size of a marble, or let's make it smaller than a marble. Let's make it a pea. If you had a pea that consists purely of the nucleus material, that would weigh 250 million tons. That's how heavy that would be. So you can tell that it's so densely packed. The nucleus is small. It's 1 times 10 to the negative 13 centimeters versus the size of an atom is about 10 to the negative 8 centimeters. Now you guys are thinking, well, 8 and 13, that's not that big of a difference. We're talking about the exponent here. I mean, which one would you rather have? 10 to the 8th money or 10 to the 13th money? Well, obviously 10 to the 13th. 10 to the 8th money is like this. That's 1, 2, 3, 4, 5, 6, 7, 8. That's what? $10 million versus 10 to the 13th. Actually, wait, no. It's $100 million versus 10 to the 13th, which is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So that is $10 million or $10 trillion. Which one would you rather have? Yeah, 10 to the 13th. Do you see how this thing is like? This thing isn't just twice as big. It's not even 5 times as big. It's like, what is that? 100,000 times bigger. So, a proton is 100,000 times bigger than an electron. That's the difference we're talking about. Okay? All right, here we go. So, remember how I told you that all atoms aren't exactly the same? If I have oxygen, I might not have exactly... If I have 2 oxygens, they might not be the exact same kind of oxygen. Does that make sense to you? Of course it doesn't make sense. You guys don't understand what I'm talking about, and here's what I'm saying. Okay, let's see. I think I feel like I'm skipping something, and I want to go back to that. Before I talk about ions and isotopes, let me kind of come back to am I going to talk about isotopes here? Let me see. 1 second. 1 second. I just want to make sure that where did they talk about isotopes? Alright. Alright, I'll tell you what. Let's do this. Yeah, let's talk about isotopes for sure. That's fine. Okay, so a hydrogen atom has 1 proton, which will make it red. Got it? And it also has 1 electron. We'll make him blue. And it's got 1 neutron. Does that make sense? Okay. So I could have a proton, 1 neutron, and 1 electron, and then that would be the hydrogen atom, right? I could have more neutrons in that atom. Now, is that still hydrogen? Yes, it is still hydrogen. It is hydrogen because hydrogen is defined as having one proton. If it has two protons, then it's no longer hydrogen. But since it still has one proton, it is still hydrogen. However, what can you tell me about it? Compare that to the regular hydrogen.
It just has one more.
It has one more neutron, which makes it what? It's heavier. Exactly. It's more massive. Because these things, like most of the mass, all of the mass from the nucleus, or from the whole atom, comes from this nucleus right here. And if you have two neutrons versus two neutrons and one proton versus one proton and one neutron, this thing is like 2/3 heavier than, or 1/3 heavier than the other one. Does that make sense? So we call different, no, it doesn't have a different charge, because charge is governed by the protons and the electrons. If I'm adding neutrons, I'm not adding any charge. I can just keep adding neutrons all I want. All I'm doing is I'm just making it more massive. I'm making a heavier version. We call that, the word for that is called isotopes.
We have to memorize this.
Yes, you should memorize this. Isotopes. Or at least understand where they come from and understand what I'm talking about here. We cool? So an isotope is not a positively, it doesn't have a weird charge or anything. What it does is it has a weird number of neutrons. Usually the amount of protons and neutrons are about balanced. There's just about the same number of protons as there are neutrons. However, this isn't always true. Your neutrons could be different. And if you have two less neutrons, then you'll have a lighter isotope of that molecule. If you have one too many neutrons, you have a heavier isotope of that molecule. You'll still have that same element. However, you'll have, a heavier or lighter version. Does that make sense to you? Okay. So, we covered isotopes. Now, you got to admit, you guys are like, okay, this makes sense. And this is a lot better than doing all the math, right? So, I mean, you're just listening to Mr. Balday tell a bunch of stories. Okay. So, we have a proton and a neutron. And if I throw in an extra neutron, what am I making?
A denser isotope.
It's not a denser isotope. It's a more massive isotope. Yeah. All right. Cool. Very good. All right. I could also, usually your elements will have a balance of charges. You'll have one positive to one negative, or 12 positives to 12 negatives. However, there's often cases where you'll have extra neutrons, or not neutrons, but extra electrons on the outside. And in that case, what is that called? Do you know? Technically, I should be finished in 5 minutes, but we'll see how far I get. All right, this is called an ion. An ion is really important. It is an off charge. In this particular case, this is a hydrogen ion that has a -2 overall charge. Why? Because there's 3 negatives and 1 positive. So it's got a -2 overall charge. This is a -2 hydrogen ion. Are we cool with that? So, if I mess with the number of neutrons, I make a what?
Ion.
No, I make an isotope. If I mess with the number of electrons, I make an ion. And if I mess with the number of protons, what do? What do I make now? I make a totally different element. It's not even hydrogen that I'm dealing with anymore. Because an element is defined as how many protons is in that thing. Does that make sense? And would you like to know where to find how many protons is in something. Okay, well, we'll do this. We'll go over here, open this up.
So the number of protons just is the only thing that changes the element. But if you add electrons and neutrons, it just changes.
Say that out loud, because I think that you're onto something. What did you say?
Can you say it?
No, you say it. You scared?
Yeah.
Okay, fine. All right, Emily was asking me, and I agree with her completely. She's basically recapping. She says, wait, so the number of protons tells you your element. And the number of, if you change the number of protons, then you change the element. Is that correct?
Yeah.
Okay. And then Emily said, if you change the number of neutrons, then you're making the same element. You just have an ion version of that element. Right? Is that what your deal is?
Yeah.
And then if you change the number of no, did I say isotope? You have a different isotope of that element.
Yeah.
If you change the number of electrons, then you have a different ion of that element. But it's still the same element. Are we cool with that? And look, see this number right here? That number 1, this number 3, that number 4.
That's the number of protons.
That's the number of protons. That actually tells you it's this many protons. So if I have 1 proton to begin with, and I threw in 2 more protons, what am I dealing with here? I'm dealing with lithium, Li. Are we cool? And if I threw in, 9 more electrons or 9 more protons, I'm dealing with magnesium. I no longer have lithium. But if I start throwing in things like, if I start throwing out stuff like, here is the number of, here's the number of neutrons, I change that, then what happens? Well, then you have a different isotope. Are we cool with that? All right, so let me kind of go off the periodic table because this is really important stuff as well. I want you to notice this number right here. 1, almost 7, 24.305. What this is saying is this is actually the mass of magnesium as it's found in nature. It's called the molar mass. Okay? And what it's doing is it's kind of, I guess maybe one way you can kind of think of it is, where does all of the mass come from in an atom? Where does all of the weight come from? I'll give you a hint. There's 3 answers. There's protons, neutrons, or electrons. Where does all the mass come from?
Electrons.
All right. Emily says electrons, and she is absolutely wrong. Tejas is wrong as well. You, in fact, not only are you wrong, you're exactly opposite of wrong. I mean, not that doesn't make sense. Your answer is exactly, the exact opposite of your answer is the correct answer. It doesn't come from electrons because electrons are so incredibly small compared to protons. Remember, we talked about it. It's 100,000 times smaller than a proton or a neutron. The electron is super small. So your mass really comes from the protons and the neutrons. Does that make sense?
Kind of.
All right. So what we can do is we can write, what I would do is I would say we have this thing that I'm going to call the atomic mass number. Atomic mass number. And it isn't exactly this number right here, 24, but it's very closely related. So what we would do is, if our atomic mass number is 24, and I told you our protons, the proton count That looks like card. Count, C-O-U-N-T. Or a better word for that is atomic number is equal to 12. Then what element am I dealing with here? If protons is 12, what element am I dealing with? I'm dealing with magnesium, Mg. Actually, it would be this. I usually write it like this, Mg, the 12. But I told you the atomic mass number is 24. What is the number of neutrons that I'm dealing with? Because if the mass comes from the protons and the neutrons, then what is the number of neutrons that I have in this magnesium?
-12.
What is minus 12? You're onto something. Say it out loud.
This is number of protons, so if you minus it, you get neutrons, right?
Yes, exactly. There we go. Say it out loud. Come on. No, why do I gotta say it? All right, fine. Look, this number up here is the atomic mass number. This over here is the atomic number. What I'm saying is this is actually the combination. This weight comes from the combination of protons and neutrons. And I know that I'm dealing with magnesium, so I know for a fact that I have 12 protons. So if I ask you how many neutrons I'm dealing with, all you do is do 24 minus 12 is 12. Does that make sense?
So there's 12 protons and 12.
Magnesium usually has about 12 protons and 12 neutrons. Are we cool? All right. Sodium. Let's look up sodium real quick. Sodium's over here. It's also known as, do you know what the equation is for sodium? Actually, it's over here. Sorry. What the letter is, the element symbol is?
Where's sodium? Can't see it.
In fact, I think that what we're going to do is we're going to start making flashcards. I'm going to make that as an assignment.
Na.
It's Na. Sodium is Na. And it is actually, the reason why it's called sodium, or that, is because it was originally called natrium. That's the word for it. So, what's going on? No, I don't want to do that. All right. Natrium, Na. Natrium is written like this. I write the element symbol. I write the atomic number, which is 11 in this case, and the atomic mass. And I hate to say it, but the atomic mass of natrium is actually 23. How many neutrons how many protons am I dealing with?
11.
11. How many neutrons?
23 minus 11.
Which is 12. Sodium occurs naturally in nature as an ion, as an isotope. I think that's interesting. It naturally occurs in nature as an isotope because it doesn't have the same exact number of protons as it does neutrons. Does that make sense to you? Now, if I toss in a few electrons in there, sure, I might make an electron with it, or an ion version of this element, but I wouldn't really change that atomic mass unit. Do you understand why?
It's small.
Because if I threw in one extra electron, it would be like comparing, oh, well, now your mass is actually 23.00000001. You added an electron, or whoop-de friggin' do, right? They're going to be like, that doesn't change anything. Your mass is the same. Essentially, even though technically, the mass does change when you add in extra electrons, essentially it doesn't really change. Does that make sense? Are we cool with that? All right. I feel like I'm going to stop here because what I want to do is I need to introduce to you the periodic table, and I think I have this really fun activity that I'm going to go look up for Monday's lecture, and it's going to be, I'm going to make it a lab. I think it will be fun. It has to do with Pokemon. Are you guys into Pokemon nowadays, or is that like...
No.
Was that big when you were a kid, at least?
I don't really watch it.
Or was that too old for you? Is that too old for you? Am I that old?
I don't know. My brother watches it.
Or is it too young for you? I love Pokemon. Good. I've got a math or a chemistry lesson I'm doing based on Pokemon. All right. Consensus is no. Fine. I'll tell you what. I'm going to make you do it anyway because Mr. Dalday worked on it so hard to try to make something fun for you guys. Last time I do that. Anyway. No, I'm just kidding. I love doing fun things for you guys. All right. Any other questions?